In this video, I would like to discuss the multiplicity of a zero for a given function and talk about how this information can help us sketch the graph of polynomial functions. So a zero of a function is simply a solution to the equation f of x equals 0. You could imagine taking a polynomial, setting it equal to 0, and solving for x. If you think about it, that's the same as finding an x-intercept, or the x value of an x-intercept. And so the words 0 and x-intercept are roughly interchangeable, although 0 is referring to the x value and x-intercept is typically referring to the entire point with an x value and a y value of 0. So given a 0, we can talk about its multiplicity. The multiplicity of a 0 is the number of times its corresponding factor appears in the factored form of the polynomial. Let's consider that with an example. So I have a polynomial function here that's already factored, and I want to find the zeros with their multiplicities. So the zeros are the solutions to this equation, x minus 1 cubed times x plus 1 squared times x minus 2 equals 0. And we know from the zero product property that we can take each of these factors and set each factor equal to 0 to find a solution for x. So I have a possible solution, x equals 1. I have another solution, x equals negative 1. And an additional solution, x equals 2. These are the zeros of x, of f of x, and they each correspond to a linear factor of x. So x equals 1 corresponds to this factor, x equals negative 1 corresponds to this factor, x equals 2 corresponds to this factor. So here's what we can say about the zeros. 1 is a 0 with multiplicity 3. Because the 0, x equals 1, corresponds with this factor that appears 3 times in the factored form of the polynomial. Negative 1 is a 0 with multiplicity 2, because the 0, negative 1 corresponds to this factor, which appears twice in the factored form. And finally, 2 is a 0 with multiplicity 1. This factor, x minus 2, appears once. It is to the power of 1 in this factored form. So there are some zeros with their multiplicities. Now, how does that help us sketch the graph of a polynomial function? A very powerful fact is that the behavior of a graph of f of x near a 0 with multiplicity n is similar to that of the graph of f of x equals x to the n. Here's what we mean by that. Look at some examples. So a 0 with multiplicity 1, the behavior near that 0 is going to be similar to the graph of y equals x to the first. That's a linear graph, right? It just passes through the x-axis on a diagonal line. A 0 with multiplicity 2 is going to be similar to the graph of y equals x squared near that given 0. Notice what's happening there. It's simply touching that 0, the x-axis, and then rebounding. It doesn't cross the x-axis there. A 0 with multiplicity 3 is going to be similar to the graph of y equals x cubed near that 0, which crosses the x-axis, right, at a slight curve, and then continues on. So this is very powerful because we can begin to describe what the graph of f of x looks like near its zeros with their given multiplicities. Let's use that information to sketch the graph of the function, same function that was given above. Remember, this has zeros of 1, negative 1, and positive 2. These are the zeros, and their corresponding multiplicities are 3, 2, and 1. Let's imagine sketching this graph, a very rough sketch. We recall from an earlier video that the end behavior of this graph is like that of y equals x to the 6th. If I think about multiplying out all of these terms in the function f of x, I'm going to get x cubed from the first term times an x squared from the second term times an x to the first from the first term. So this, in its expanded form, is going to begin with x to the 6th, and then there will be a lot of other terms here following. But the end behavior of the function depends only on its leading term. So what does the graph of y equal x to the 6th look like? Well, it goes upward in both directions. The y values are increasing as x goes to infinity, or going upward as x goes to negative infinity. So we have the end behavior, and now let's record this information about the zeros. The zeros are at 1, at -1, and at +2. And here's what we can begin to say about this function. For the 0 at +2, because there's a multiplicity of 1, the graph is going to appear linear right near that 0. For the 0 of +1, there's a multiplicity of 3. The graph is going to appear cubic near that 0. So it's going to go up through this 0 in this shape. And for the 0 of -1, there's a multiplicity of 2. So the graph is going to appear quadratic near that 0. It's going to touch the x-axis and then rebound. And so we're beginning to sketch a rough shape of this graph. There's some things we don't know. We don't know where this local minimum value lies. I'm just going to fill this in using some imagination. We don't know exactly where this maximum value occurs, but piecing together what we do know about the zeros and about the end behavior, we have a rough sketch of our graph.